All right, here we go with topic 5.2, Intro to Rate Laws. So far, you have looked in this section at reaction orders and determining the order of a reaction. The order of a reaction is just a way to see how a specific element or compound or chemical in a reaction affects the rate of the reaction. So let's just review that so far. If a chemical or in a reaction is zero order, then that chemical is raised to the zero power in the reaction. Remember, the brackets around a chemical mean concentration, so the molarity of it is raised to the zero power. Anything raised to the zero power is 1, so we can simplify the rate law to rate equals K. So that means that that chemical has zero effect on the rate of the reaction. So that's why our rate law can be simplified to rate equals K. It's equal to our rate constant. If something is first order, then that chemical is raised to the first power, which we don't have to write. We know it's raised to the first power. And that means that whatever we do to that chemical is going to have a direct relationship with the rate of the reaction. If I doubled A, the rate would double. If I tripled the concentration of chemical A, the rate would triple. If I made A 1,000 times bigger in its molarity, the rate would go 1,000 times faster, okay? They're a direct relationship. If a reaction order is second order, so for an individual chemical, if it's second order, then whatever we do to that chemical, it's going to have a larger effect on the rate of the reaction. So for instance, if I made chemical A twice as big, so I had 2A, 2 squared is 4, so that would make my rate 4 times faster. Or if sorry about the bell, if I made A triple the amount that it normally was, 3 squared is 9, so my rate would be 9 times faster. So it has this squaring effect. Now we can have a rate law that is first order with multiple chemicals, so it's second order overall. So each individual chemical would have its own effect on the rate of the reaction, but together they would have that second order effect on the rate. Now, the other things given here are your units for your rate constant. Now, you'll notice they're not all the same. It is going to change depending on the order because our rate, the units for the rate always have to be the same. So if we're multiplying the rate constant by different things, then its units are going to need to change so that our units stay the same for the rate on the left side. Okay, and this is a reference. We're going to see how we calculate and get these units. But let's look at them. We've got molarity per second. Molarity per second, they would be the same for for zero order reactions because the rate equals K, so their units should be equal. You can also write it molarity times seconds to the -1. We can write them either way, so that's something to keep in mind. For first order, the molarity goes away. We have 1 over seconds or per second, or seconds to the -1. But again, our units for the rate on the left side stay the same. If it's second order, our units for our rate constant K is 1 over molarity times seconds. Okay, or we can write it as molarity to the -1, seconds to the -1. So there's multiple ways we'll see it written, something to keep in mind. The other way you might also see it, instead of them writing molarity, they might also write, so say it's molarity per second here. They could write moles per liter times seconds, or that would also be written as moles times, they might write liters times seconds to the -1, something like that, okay? So those are other ways you might see this same one, is instead of writing molarity, they write it as moles per liter. So, things to keep in mind. Now, what we're going to be looking at here is how do we come up with a rate law? How do we get these? How do we know what the order is? How do we calculate it? Also, how do we calculate our rate constant? So, we're going to go through an example, a couple of examples here where we do the whole process, okay? So let's take a look. The following data was measured for the reaction of nitric acid with hydrogen. So we got nitric oxide with hydrogen, not acid. And it gives us nitrogen and water, nitrogen gas and water. We've done 3 experiments, and we can see that we've altered the concentrations of our nitric oxide and our hydrogen with each experiment, and we've measured the initial rate of the reaction, what the rate is to start. Now, you guys have practiced looking at data like this and finding the order for the reactants. We're going to take a look at another way we can do it, but you can, and I'm going to give you multiple options on how you can solve. It is your choice how you want to show it, okay? You have some freedom there because it's whatever clicks in your brain and what works for you. So, the best way to start these is to write just a general generic rate law for the reaction so you have something to refer to. So it's always rate equals K times your concentration of your first reactant to some sort of power, I'm going to put X, times our second reactant, hydrogen, to some sort of power, I'm going to put Y. Okay? You do have to write rate equals. This is a part that students like to leave off. If you don't write that, you have not written a rate law, you've not written an equation or an expression, you've written part of it. Okay? You have to write the rate equals part. Okay? So if you need to make a little note to yourself to write the full equation, do that. Now, just like we practiced, we're going to take a look at our experiments. It says compare 2 experiments where NO changes and H2 stays the same, because part A is to determine the reaction order with respect to NO. So basically, we're going to solve for X. Okay, we want to solve for X. So we want NO to change. So we can do 1 and 3 or 2 and 3. And we want H2 to stay the same. Well, H2 stays the same with 1 and 3. So I'm going to do experiments 1 and 3. Now, plug in the values. It says set up a ratio of the 2 experiments, larger initial rate on top. My larger initial rate is going to be experiment 3. So I'm going to be comparing experiment 3 and experiment 1 with experiment 3 on the top. Now, we're going to plug in the values. So all the values for experiment 3, all the values for experiment 1 into our rate law. We have an equation to plug it into, so that's what we're going to do here. Oops. So my rate for experiment 3 is 4.92. My units are molarity per second. And rate equals K, which we don't have, so we're just going to put K. Anything we don't have, we just leave, times my concentration of NO, which is 0.20, to the X, my concentration of hydrogen for experiment 3, 0.10, to the Y. Now these are also both molarity. Your units there, they will cancel. I won't throw that out there, but they are molarity for each of those. So I've plugged in my 3 values for experiment 3. I don't have K, I don't have X and Y. Those are going to stay as is. Now, I'm going to divide all of that by experiment 1. So same idea. 1.23 molarity per second equals K. Both of my concentrations are 0.1 to the X and 0.1 to the Y. So here's the fun part. We get to cancel a lot of things. So we basically set up a fraction. Well, things that are similar on the top and bottom, we can cancel. So starting from the left, I can get rid of my units here. If I had my units for molarity on these 2, I could also cancel them for my molarity too. K is the same. That can cancel. These are not the same. They cannot cancel, but 0.1 times to the Y and 0.1 to the Y are exactly the same. So all of that cancels. Now, we've canceled a bunch of stuff, and now we can simplify. So I've got a couple of fractions here that I can simplify. I've got 4.92 divided by 1.23. Okay. If you want to see this as a simplified version, I'm going to show you that real quick. But we can kind of jump ahead and solve this part. So let's just look at what, if we brought down the pieces that we still have, that's what it would look like. Okay, so now I'm going to go ahead and divide this part, and I get 4. 0.2 to the X over 0.1 to the X, so 0.2 divided by 0.1 gives me 2, but it's still to the X power. Now I can solve for X, right? So 2 to what power gives me 4? Well, 2 squared is equal to 4, so X is going to equal 2, because 2 squared equals 4. Sorry, my weird dot. So x equal 2. Well, what does that mean? That means that it is second order with respect to NO. Okay, so since x is 2, the reaction is second order with respect to NO. All right, so that is one way we can approach this, is to solve it using our rate law. We can always solve it, okay? As a side note, and I'm going to do this as a sticky note on top, so that you've got that as an alternative option, is we can do it in a sentence, okay? So if I look at my data up here and I say, okay, I'm going to compare experiment 1 and 3 because this one changes and this one stays the same. In my initial rate, we can see, I do a little side calculation. I'm like, okay, well, my rate is 4 times bigger, so that one is times 4 when this is times 2. Okay, when that happens, right, 2 squared is 4, then I know it's second order. Okay, so I can just say when the concentration of NO is doubled, the initial rate is 4 times faster, keeping the concentration of hydrogen constant. This makes it second order for NO. And I can state it in a sentence or 2 sentences in this case. This is just as good as this. Both of them are valid, both of them work. If you can look at this and figure it out without setting up a calculation, and you can just write it out in words, go for it. Okay, you do not have to show the math, but if you're more comfortable with the math, go with it, okay? So that's how we can approach this in 2 different ways. So I'm going to show both ways for the next one as well. Okay, but I need to move this sticky note out of the way. So you can always pause and go back and write that down if you need to. Okay, let's try our second one. I'm going to change up our colors so we can tell the difference of what's going on here. And we want to pick now, we want to determine the reaction order with respect to hydrogen now. So that means that we need hydrogen to be changing and NO to be staying the same. So NO stays the same with experiments 1 and 2. Hydrogen does change, so we're using these 2. I'm going to show you mathematically how to do it, and then we'll do it in words. Let me scooch this up a little bit. So, mathematically, we're comparing experiments 1 and 2. Experiment 2 has the larger value for hydrogen. Their initial rates are the same. So I'm going to put experiment 2 on the top, experiment 1 on the bottom, and we're still plugging into the same rate law. Okay, that doesn't change. So we've got experiment 2, its rate is 1.23 molarity per second. Rate equals K times the concentration of NO. Those are going to be 0.1 for both. And you can still put X, or you could put that it's a 2 now that we've solved for X. Either one, it will end up canceling, so that's helpful. And this is 0.20 to the Y. We're going to divide by our experiment 1. It has the same rate. Rate equals K, same concentration for NO, and this one is 0.10 to the Y. So again, this is where we get to cancel everything. So we can cancel our units, we can cancel K, we can cancel this. So we're down to 1.23 over 1.23 equaling 0.2 to the Y over 0.1 to the Y. And we can simplify. 1.23 over 1.23 is 1 equals, this reduces to 2 to the Y. So what to the, or 2 to the what power gives us 1, anything to the 0 power gives us 1. So y equals 0. So it's 0 order. So since y equals 0, the reaction is 0 order with respect to hydrogen. Okay? So again, I'm going to show you how to write this out in a sentence for this one. So again, when I look at this, I'm seeing that NO stays the same. Hydrogen doubles, but nothing happens to my rate. My rate stays the same. So what does that mean? We can write it out for part B. When H2 is, or the concentration of H2 is doubled, the initial rate does not change. While keeping NO, the concentration of NO constant. This makes it 0 order for hydrogen. Right? So when we double hydrogen, when we change hydrogen, nothing happens to the rate, has no effect, making it 0 order, 0 effect. So we've got two options. We can use sentences to describe it, or we can use math to describe it. If you feel more comfortable, maybe you notice it's 0 order and you can just write that one out in a sentence easy, but you need to calculate the other one, that's fine too. You can mix these up as long as you're showing some sort of justification for your answer. That is the key to all of this. Now, we've got a little more building off the same question on the next page. So it says, now that we've solved for those, we can write the rate law for the reaction and include the orders. So now we have rate equals K times NO, second order, and we can put H2 to the 0 order, or we can rewrite this rate equals K times NO squared, right, to the second order. Either of those is fine. You don't have to include hydrogen if it's to the 0 order, but we need to remember that it's still there. It's still in the chemical reaction. So if you're ever given a rate law like this, and they ask, what's the order with respect to a chemical that's not there, then you know it's 0 order because it's been eliminated. And now it says calculate the overall reaction order for this reaction. Our overall order is our x plus our y, so it's 2 plus 0 gives us second order overall. Okay, so we're just adding up those exponents, nothing too crazy there. All right, calculate the rate constant. This is where we can solve for K. Now it says rearrange the rate equation to solve for K. Pick a set of experimental data, plug in, and solve for the value of K. Keep track of your units. So we're going to first write our rate law, and I'm going to go ahead and leave out my hydrogen since I don't really need it. It's going to simplify my equation. And I want to solve for K. I want to get K by itself. So I'm going to divide by NO squared. I'm going to do it on both sides. That cancels. So then my rate equals K, or my rate over NO squared equals K. Okay, and I'm going to plug into that equation, okay? So this part here is my equation. Now, it says pick an experiment, a set of experimental data, and plug in and solve. So we have 3 experiments. It does not matter which one you pick. I always pick the first one because it tends to have the easiest numbers, but pick the one with the easiest numbers for you. We're going to take those values. So for in this case, we need a rate and we need the concentration of NO. So concentration of NO, rate, and I'm going to plug them in. All right. So my rate is 1.23, and you've got to include your units. That is non-negotiable at this point, because this is a place where they love to ding you on your units. Okay, we have to show the correct units. So this is 0.1 molar. This is molarity per second. We have to square that to get our rate constant. Okay, so let's talk about that. We got 1.23 over 0.1 squared. So how am I going to put that in my calculator? Well, I'm going to put 1.23 divided by, I'm going to put parentheses, 0.1, square it inside the parentheses, so the only thing being squared is that number. So it'll square this, and then it'll do the division, okay? And I'm going to hit enter. 123. Fabulous. I got 123 equals K. I need units. So let's look at them. I'm going to pull my units over here and look at them a little closer. Molarity per second on the top, divided by, my molarity is also squared. It doesn't just square the number. It's just like having 2x squared, right? The 2 is squared, the x is squared. That whole thing is. So now I've got molarity squared on the bottom. One of my molarities can cancel. The one on the top cancels with one of them on the bottom. Now I basically have two fractions here. I've got molarity over seconds, so these seconds are on the bottom, and this molarity is on the bottom. Usually we put the molarity first, second second, but either way works, so 1 over molarity times seconds. Okay, let's check this. This is a second order reaction overall. If we go back to our units on the first page, second order overall, my units for my rate constant should be 1 over molarity times second. And I've shown that here and calculated that. If you want to take the time to memorize all this, go for it. Or you can just learn to calculate it and get your units. Okay. The calculations aren't super complex. It's just taking those steps to write everything out and be meticulous about it. All right, our last question here says calculate the rate. So we're finding rate. When it says calculate the rate, we're looking for that word rate. When NO is 0.05 and hydrogen is 0.15 molar. So now we're given two new concentrations. These are different from what's in our experiment. We want to know the initial rate of the reaction. Okay, so this is like running a fourth experiment with new concentrations. Well, we can calculate that now because we have our final rate law and now we have our rate constant. So now we can calculate the speed of the reaction, the rate of it, at any concentration of our chemicals. Now, we're going to plug in straight to our rate law. So rate equals K, which is 123, 1 over molarity times seconds. And then I've got NO. My concentration of NO is given right here, 0.050 molar. And I'm squaring that still. Always got to square it. Now, my hydrogen is also given, but it's 0 order. So if I plug this in and raise it to the 0 power, I'm going to get 1. So I don't really have to do it. Okay? If it makes you feel better to plug that in, it's fine too. Your molarity is also to the 0 power, so it goes to 1 as well. So this whole term is 1. So if we calculate now, again, 123 times, I'm going to put this in parentheses, 0.05, and square it inside my parentheses, so that's the only number being squared. And I get 0.3, and I've got, it looks like 2 significant figures here, so I'm going to do 3, 1. Now let's just experiment with this. If this was 123 and I did times 0.05 squared, we do get the same answer. Okay. I guess I'm proven wrong on that. I wonder if the division works out, because I always get nervous about squaring things weirdly. You do get the right one, so I guess you don't have to put it in parentheses. Proven wrong. All right. Whatever makes you feel better. So be careful with those. Experiment with it with your calculator. All right, units. Units. So I've got 1 over molarity times seconds. So I'm going to work those out again over here. 1 over molarity times seconds times molarity squared. So this is kind of doing this step up here, but backwards, right? So now one of my molarities here cancels, and I got molarity over seconds, because these are still on the bottom. Molarity over seconds, which is our units of rate. So the rate of the reaction would be 0.31 molarity per second. So this is how much will react per second of the reaction. So that's how we can kind of work through all the different possible pieces of this. Are you going to be asked every single piece on every single question? Not necessarily, but you could be. Now, let's look at a second one and see how it might be a little bit different in its setup of the question. So you'll notice it seems a little bit shorter. It says write the rate law for the reaction, calculate the rate constant, calculate the rate. So it's like, it feels like they jumped to part C, E. C, there's no D, I guess this is D. That part's D. So they did part C, E, and F. Well, you can't do part C without solving for your orders. So when it says write the rate law for the reaction, it's not asking for really a generic rate law. It's asking for the rate law of the reaction. You've got to calculate your orders at that point as well. So you can do your calculation, or you can write it out in words. I'm going to show my calculation so you guys can see some more examples of that. What I always like to do, again, is still write my generic rate law so I have something to refer to. Rate equals K. My chemicals are NO to some power, O2 to some power. Oops, Y. You can use any variables there. It doesn't matter what letters you use. So I need to find what X and Y are. So you can do some analysis on it. We can see that we're doubling some of our concentrations, and we've got some changes happening with our initial rates. But I'm going to go ahead and calculate. So I'm going to do it for NO. So my order for NO is what I'm going to do first. So that's solving for X. When I want to calculate this one, the other one needs to stay the same. So I need to use experiments 1 and 2 for all of those. So experiment 2 is larger than experiment 1. So I'm going to put it on top. So experiment 2, I've got rate is 1 times 10 to the negative 4 molarity per second equals my K value times my concentration of NO, 0.020 molar, to the X, and oxygen, 0.010 molar, to the Y. I'm going to divide by my other one, 2.5 times 10 to the negative 5, so molarity per second equals K, 0.010 molar, 0.010 molar. All right. To simplify this, right, I can go ahead and change this up. I can cancel things out. This whole term goes away. So I got 1 times 10 to the negative 4th and divided by 2.5 times 10 to the negative 5th. I'm going to go ahead and calculate that instead of rewriting it, because then I can just simplify. Okay, so when I divide these two numbers, I get 4. When I divide these, 0.02 over 0.01 gives me 2 to my power of X. X is going to equal 2 squared is 4, so it's going to be second order. So I know X equals 2. All right, now I'm going to do my order for O2. I'm going to do it the same way. So for oxygen change up the color here for oxygen. So we want NO to stay constant, so that's experiment 1 and 3 for O2 to change. So we're going to do those ones. So experiment 3 is bigger than experiment 1. Experiment 3's got 5 times 10 to the negative 5th. 0.010 X, 0.020 to the Y, and we're going to basically do the same bottom as that one, -5, X, and 0.010 to the Y. Okay, let's look at what cancels. This whole term, K's cancel, molarity per second cancels. When you see that your exponents are the same, 10 to the negative 5th, 10 to the negative 5th, you can also cancel that part out. So what do we got? 5 over 2.5 gives me 2. 0.02 over 0.01 gives me 2 to the power of Y. So y has to equal 1. So this is first order. So we got a second order, we got a first order. So really, to answer part A, my rate law is rate equals k times NO to the second and O2 to the first. You don't typically write the 1, you leave that off. Part B. Now we want to find our rate constant k. If I was to do this, by the way, with sentences, something I could say for the first one, NO, I would say the order with respect to NO, let me go back, kind of structure it the same way as our sticky notes. So when NO is doubled, the initial rate is 4 times faster. If you ever need to do that, you just do your bigger one divided by your smaller one. You'll figure out how much faster it is. So this is 4 times when this is 2 times faster. So when the concentration of NO is doubled, the rate is 4 times faster when O2 is kept constant. This means it's second order with respect to NO. If I did oxygen, when oxygen's concentration is doubled, the initial rate is 2 times faster when NO stays constant. So the reaction order is first for oxygen. So you could do it in sentences just like the other ones, whatever you're more comfortable with. All right, for part B, we want to solve for K. So we're going to have rate over, we're going to divide by these two things to get K by itself, NO squared times O2, and that's going to be our K value. So again, we're going to pick an experiment and plug it in. It does not matter which experiment you choose. I'm going to go ahead and just go under here. So K is equal to, I'm going to do experiment 1, 2.5 times 10 to the negative 5th. Keeping track of those units, super important here. Over, we have our concentration of NO is 0.10 molar squared. O2 is 0.010 molar as well. Now, here's the nice thing. On the bottom, this is kind of like having x squared times x, so you really have the same number to the third power. So we can calculate it that way. So 2.5 times 10 to the negative 5th. I'm just going to hit enter so that's in my calculator. I'm going to hit divide. And 0.01 to the third power, right? So that takes care of the entire denominator. And 2. So K is equal to 22. Now we got units to deal with, right? We've got 1 molarity here and 1 here. Those will cancel. We've got nothing on the top now. We've got seconds on the bottom and molarity squared on the bottom. So molarity squared times seconds. Now overall, this is a third order reaction overall because second plus first gives us third order overall. A kind of little trick here is that your amount of molarity on the bottom is 1 less than your order. So if it's third order overall, I'm going to have molarity squared. If it's second order overall, I'm going to have 1 molarity on the bottom. If it's first order, I'm going to have no molarities on the bottom. 0 order, it's the same as rate. Okay, so that's a little trick I've noticed as well. Way to check your units. So that's our rate constant there. And then we have part C, calculate the rate in molarity squared when at the instant when NO is 0.015 and O2 is 0.005. So now we just plug in our all our values. So 22, 1 over molarity squared times seconds. NO is 0.015 molarity squared because it's second order. And then 0.0050 molarity to the first power because it's first order. And then we calculate. So we have 22 times 0.015 squared times 0.005. We get this lovely answer. I'm going to put it in scientific notation. So let's see, we've got 2 sig figs on everything. So 2.5 times 10 to the negative 5th molarity per second, right? Our molarity squared cancel. We're left with 1 molarity on the top, seconds on the bottom. So that is how we can solve rate law equations, find our rate law, find our orders, find our constant, and then we can solve any type of question. If we're given things like it says, oh, and it's this order for this chemical, maybe it skips a step for you and gives you one of them. That's really helpful. Sometimes they'll just give you the rate law and then you're solving for K, or you're solving for a rate like this one. Sometimes it's just about finding your orders. So we've done all the pieces, so you can do any piece that's asked for. All right, I know this is a long video, but you've got lots of details there. Let me know what questions you have. Thanks.